So science has a lot of prestige, and especially over the last couple of 100 years, with the development of technology, especially let's say electricity and all the gadgets which run on electricity. Science now just amazes us. We look at the sky and there's a plane flying, and that's science, right? Didn't really happen earlier. Okay. So science has a lot of prestige, and people tell each other, be scientific. So, what is science and what is not science? Well, science requires three things. Variables can be measured numerically or alternatively described very accurately. So, they mean the same thing to different people. Okay, if I say mass and I say this book weighs 3.27 pounds, as I know because I mailed this book and I had to pay for 3.27 pounds. So when I say this book weighs 3.27 pounds, or I say its mass is, let's say, 1.5 kilograms. Of course, weight is a unit of weight is force, whereas kilograms is mass. Okay, so when I say that, it means the same thing to everybody. So that's the first requirement of science. The variables are defined very accurately, and therefore they mean the same thing to different people. It can be measured numerically, or they are still, without being measured numerically, they can be described accurately. For example, the structure of a protein, very accurately described. The second thing about science is that the variables are sparse. You don't just you want to answer some questions, you just don't go and make up some variables and say, okay, I'm defining this variable to mean this thing and that variable to mean that thing, and I'm going to find a relationship between these variables. No, that's not how you do science, because science, the set of variables is sparse. It only has a few variables. Physics, you have mass, you have force, you have distance, etc. Then in science, we make hypotheses about causal relationships between these variables. For example, force causes acceleration. So that's a causal relationship. And in my book, there is a lot of analysis which gets into force and mass and acceleration, because I'm trying to calculate the paths of spacecraft. Okay, so the hypothesis which I rely on for that, for those calculations, is force equal to mass into acceleration, or acceleration equals force divided by mass. Now, that was a hypothesis. Galileo first kind of thought, why is distance proportional to the square of time? The distance of a ball rolling down an inclined plane, why is it proportional to the square of time? And then came Newton, who was working on infinite series and such like, and had developed calculus. So you have calculus plus Galileo's observations, the laws of motion fall right out. So, so this is a very well-tested hypothesis that acceleration equal to force divided by mass, and now it's a law of nature or a law of motion. Progress happens in science because different scientists can communicate accurately with each other and build over previous work. And that leads to more complex theories over time, which explains the world with greater accuracy. For example, we progressed from the laws of motion to relativity. Okay. Now, precision, I said you need precision in science. Now, precision can be quantitative or non-quantitative. Force and mass are examples of quantitative variables measured precisely. The structure of a DNA or the stages of a star are examples of non-quantitative precision. Example of a non-quantitative, non-precise variable would be happiness, satisfaction, etc. Okay, now another example of non-quantitative precision is like, for example, what causes malaria? Malaria in humans is caused by protozoan parasites of the genus Plasmodium, etc. It's very precise, very useful, but non-quantitative. Okay, next we have, due to its ability to explain parts of the real world, science has a lot of prestige. To acquire some of that prestige, researchers in human affairs often follow a process of defining variables, collecting data, running regressions, etc. Doesn't really work. Lots of ad hoc variables are defined and conclusions drawn from statistical analysis of data. But the hypothesis and the conclusions and the method followed to arrive at this conclusion is a stretch. You can define variables which and then make like causal relationships, and however these variables may lack the characteristics of science, which is that they have to have precision and there are few and not many variables. And these causal relationships may actually be true. And in human affairs, the causal relationships are not amenable to discovery by the scientific process. However, human affairs are supremely important. For example, a causal relationship in human affairs, very often discussed in my book, is that we need to feel that we have done our duty if we wish to have the best possible life. So duty is not something that we do just for others, it is something that we do for ourselves also. We do it for others and we also do it for ourselves. It is true. This is a causal relationship. It is true. However, you can't go around measuring duty and you can't go around measuring the best possible life and then running a regression. That's not going to happen. Okay. Very important, but not amenable to the scientific process. So if you don't have the scientific process, how do you go about discovering the truth about these hypotheses and these relationships? Well, you have to rely on wise people. And that is wisdom rather than science. And you just have to see who is wise, and then see what they're saying and live your life accordingly.